All right, wish me luck. We're doing 843. There's some big problems in here, and I am flying blind. It's late. I'm tired. I want to knock this video out. I should do these problems before I start, but I'm not, so wish me luck. All right, so while Earth's orbit around the sun is slightly elliptical, it can be approximated by a radius of 93 million. All right, 93 million for a radius. How far does the Earth travel in one orbit around the sun? Well, I am looking at circumference. So circumference is going to be 2 pi times 93 million. So obviously that's going to be 186 million pi miles. Hardly at all. If you think about how fast you're moving right now, it's crazy. Like, the Earth is moving, and we don't even feel it. Gravity's a heck of a thing. That's supposed to be pi miles. Okay, approximately how fast is Earth? Well, there you go. How fast is Earth traveling in its orbit in space? Calculate your answers in miles per hour. Well, if I'm going that many miles, I want to divide that 186 million by how many hours there are. If that's a year, 1 year has 365 days at 24 hours per. So 365 times 24. It appears there's 8,760 hours in a year, so I'll divide this by 8,760. So 186 million divided by 8760. I'm getting the wrong answer. I knew I shouldn't have done that. Okay, approximately how fast is the Earth traveling its orbit in space? Calculate your answer. Oh, because this is pi. Shoot, that's pi. So I need to multiply that by pi. And we're going to get, so that's 186 million pi divided by 8760. So I apologize for missing that. But we're going to get 66,705 miles an hour. So if you think about that, that's insane. That's how fast I move as I come up with this video. All right. A certain car's windshield wiper clears the proportion of the windshield in the shape of 120 degrees. So if the windshield wiper pivots 120, what's the area that it hits? Well, here's what I'm going to do. I'm going to say this radius is 20, right? And that's going to give me the whole thing, including the part that misses, right? So then what I'll do is I'll come back and I'll do 1 of 5 and I'll subtract. So again, it's going to be pi r squared, and I'm going to use 20 for the whole thing, pi r squared times 120 over 360, which is just 1 over 3 anyway. And I'll go minus pi r squared times 120 over 360. So essentially I'm saying, all right, give me the area of this whole thing, and then subtract out this part of it. And then what will be left is the part that I want. So I'm going to get 400, 20 times 120, so 400 times 120 divided by 360. So I'm going to get 133 pi. And I'm going to subtract it by 25 times 120. Divided by 360 minus 8.33 pi, right? This is 33, this is like rounding. So I'm going to get 125 pi. Or, it's inches squared, right? Is this in inches? Yeah. Or if I want, I could do what I forgot to do up here. Man, oh man, I'll tell you, my handwriting is poor. I can do what I forgot to do up here and multiply that by pi and get 125 times pi, and I get 390, essentially about 393 inches squared. So Either way, again, this is an actual amount. This is an estimated amount. Alrighty, so moving along. The cookie cutter. A cookie baker has an automatic mixer that turns out a sheet of dough in the shape of 12-inch squares, 12 inches wide. His cookie dough cuts 3-inch circular cookies. The supervisor complains that too much dough is being wasted, orders the baker to find out what size cookie would have the least amount of waste. So when he analyzes the situation to determine how much cookie dough is wasted when 3 inches are cut, and then have the team calculate the amount of dough wasted when the other is cut. So, waste when 3-inch cookies are cut. So 3, 6, 9, 12. So these have a radius of 1.5. Right? 1.5. So I think what we do is we say, all right, well, this whole cookie sheet has 144 inches squared, 12 by 12, right? Each of these little cookies has an area of pi r squared. And again, these are 3 inches across, so the radius is 1/2. So we're going to say 1.5 squared. We'll multiply it by pi, by 3, I'm sorry, by pi. And we get 7.06 inches squared. Well, obviously there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 cookies, right? Because this is a square. So we'll multiply it by 16. It's 113 inches about. That's how much we're using. So our waste will be whatever this subtracts to. So 144 minus 113.09. So it looks like our waste is 30.91 inches squared of waste. So now let's go ahead and what if we made 6-inch cookies, right? So if we had 6-inch cookies, we'd have a lot less of them. Our sheet would look something like this. 6, 6, 6, 6, right? So our radius here is going to be 3. So we'll go pi r squared. That'll get us 9 pi. So again, we'll multiply 9 by pi. That gives us 28.27. But the problem is we only have 4 of these things. So we'll multiply that by 4. And oh my goodness, we get 113.09, which should look familiar. So it turns out that we have the same amount of waste if we go with this cookie. What if we go with a giant 12-inch cookie, right? So our radius is going to be 6 inches. So we'll say pi r squared. We'll get 36 pi. And guess what 36 times pi is? It's 113.09. So we'll still have 30.91 inches squared. So as long as you're not making weird shaped cookies where like it doesn't reach the edge, right? So like we could have done 4-inch cookies. We could have done this as well if we wanted. And we would have gotten 9 cookies out of it, but we still would have had the same amount of waste. It doesn't matter, oddly enough, which is kind of surprising. In that situation, it's irrelevant. We get the same amount of waste. All right, so remember the radian measure of an angle is the ratio of the arc length to the radius for the corresponding sectors, which, by the way, I should have said in the other one, I had like an extra r, and I wasn't sure why. Well, if you'll remember, it's because we were supposed to do the ratio of the r. So it was like pi r over 6, but what was supposed to happen was we were then supposed to divide by r, so those r's, that's where we're getting the pi over 6. I kind of forgot that in the last video, and honestly, I didn't care enough to go put that back in, but if you were ever wondering, like, oh geez, that was really weird, Oliveira, that's what happened. Skipping the video there, I think it's got away from me a little bit, so I kind of clipped the video and came back and went again. So, all right, so what's the radian of a measure of 45-degree angle with a radius of 5? So if we have a radius of 5, and I think part of my issue is sort of running out of room, So I'm going to give myself a little bit of room to kind of do this problem with. Okay, so if we have a radius of 5, what's the ratio? So remember, the other one was pi over 6. So when it was 30 degrees, we had a radian that was pi over 6. So what's the radian if it's 45? So we're going to say it's 2 pi r over 45 times 360. And again, it's going to be 10 pi times 45, so 450 pi over 360. I could drop the zeros, and then I know, hey, look, 9 goes in 45 times. I'm sorry, 9 goes 5 times into 45. 9 goes 4 times into 36. Now I want to divide this by the radius of 5. And again, we don't want to write it like that, so it's going to be 5 pi over 4 divided by 5 over 1. But again, we don't divide fractions, so we'll multiply by 1/5, and we're going to get pi over 4. Well, now it says, what about if it's 1 centimeter? Well, same thing. If the radius is 1, we're going to get circumference of 2 pi r times 45 over 360. So we'll get 90 pi over 360, which of course cancels to be pi over 4. So our radian for 45 degrees is going to be pi over 4. Again, so 30 degrees is pi over 6, 45 degrees is pi over 4. And again, both of these are going to use an integrated 3, not really using an integrated 2 at all. So we're just sort of getting you guys ready for what's coming down the road for you. So it says the central angle of a circle has a radian of pi over 3. What's the measure of the angle in degrees? So we can kind of work backwards on this one, is essentially what they're saying for us to do. So if it's going to be pi over 3, what is the angle going to be? Well, on the other one, we'll just say the radius is 1, right? So we'll just say it was 2 pi r. We'll say the radius is 1 to make it easy. So 2 pi r gives us 2 pi. We want to multiply it by a certain angle, we'll call it theta, over 360. That's going to give us pi over r, right? So what is this angle going to have to be? Well, I think we're going to have to end up at 120 over 360, right? Isn't 120 over 360 going to equal a third, which is where I want to end up? That's essentially a third. So how am I going to get this thing to equal? I think if theta equaled 60, right? If this was 60, now I'm getting 120 pi over 360, which turns into 1/3 pi. So this would have to be 60 degrees. I got to be 100% honest. I don't know how much this is really going to help you guys this year. Definitely going to help you more next year. Hopefully you'll remember this radian discussion. If you're super confused, feel free to ask me. But it's not going to be on the test or anything. It's not going to be like super germane to what we're going on with that. So let's keep going. Looks like I need to dump this and start on 104. So let's go ahead and go to this, and we will annotate the last one. I'm excited to be done with this tonight. Apparently 104 was a short question, and it was on that page. All right, so the radian measure of 90 degrees is pi over 2. What is the radian measure for 100 degrees? Well, all right, so a lot going on with this problem, but essentially what they're saying is this. 180 degrees over 360, right? And we know we're going to have 2 pi. So we're going to get 360 pi over 360. So it looks like 180 degrees is going to equal pi. Again, I don't know how much this is going to help you guys. You're going to do this next year. I'm way more concerned about the sectors and arcs than I am about the radians. You'll have a huge discussion about that with either Bauer or Baldwin or whoever's teaching integrated 3 or advanced 3 at that point. All right, let's wrap that up. Have a good one.